So Wednesday session was all about valence electrons and Lewis dots and ionic bonding and how do we make those charged particles out of what we've got here. Covalent bonding, on the other hand, we're talking about sharing electrons. And so where we see covalent bonding most often is in substances, elements that have lots of valence electrons, and that would be nonmetals in particular. Nonmetals have anywhere between 4 and 8 valence electrons. Obviously, the ones with 8 valence electrons aren't going to do any bonding because they already have the 8 that they're looking for. But if they have 4, 5, 6, and 7 electrons, they're going to be much more prone to sharing. And furthermore, if we look at it from the standpoint of our Lewis dot structures, as we were doing on Wednesday, what we can see is that when we have unpaired, you guys can't see any of that. Frozen? Okay. Wish somebody would have said something a little bit sooner. I'll be sure to post the announcements at the end so that you guys can take your pictures of it. I was wondering why nobody had their phone out. Okay. What we can see is that these electrons here, these unpaired electrons, whenever we have unpaired electrons in our Lewis structures like this is usually a prime place for a covalent bond. We can think of covalent bonding in a lot of ways as the pairing up of unpaired electrons in elements. And so from that standpoint, we can look at something like carbon with its 4 unpaired electrons, and we can say, oh, carbon is probably a really good covalent bonder. It's got 4 unpaired electrons. It can make 4 different covalent bonds. And obviously that would change as we went to looking at things like nitrogen, which has 3 unpaired electrons, or oxygen that has its 2 unpaired electrons, or even something like chlorine, where it only has the 1 unpaired electron. And so what we can see is that as we go toward the noble gases, what we also see is that the variety of bonding increases. Carbon tends to be an exclusive covalent bonder, because to be an ionic bonder, it would have to either gain 4 electrons electrostatically or lose all 4 of those through ionization energy. It's not impossible, but it's pretty difficult. Nitrogen, on the other hand, yes, we can form the nitride ion N3-, but we'll find that nitrogen forms far more covalent compounds than it does ionic compounds. By the time we get to chlorine and oxygen, we'll see that there's a great variety of compounds that they can make. Oxygen makes lots of covalent compounds. It also makes lots of ionic compounds. Chlorine and fluorine and all of the other halogens, they make lots of both. As we go further and further toward that noble gas configuration, we get more and more different kinds of bonding possible, because now it's not as difficult. It's not too difficult for chlorine to acquire 1 electron. It's not too difficult for oxygen to acquire 2 electrons and do ionic bonding. And it certainly isn't difficult for either of those to match up those unpaired electrons with other objects, other elements, to make a covalent shared bond. So let's look at some trends then. When we have these shared interactions, those electrons in that shared interaction count toward the octets of both atoms in that bond. So if I draw, for example, a pair of chlorine atoms bonding together, right now we would say that this chlorine has 7 electrons and this one has 7 electrons. If they share their unpaired electrons with each other, what they now have are the 6 electrons that are exclusively theirs. So it'd be these 6 plus the 2 that they are sharing for a total of 8. And the same thing for the other chlorine. This chlorine on the right has its 6 unshared electrons plus the 2 electrons that it is sharing for, again, a total of 8. So sharing electrons means that those electrons in that covalent bond count for the octets of both of the atoms. And depending upon the needs of each individual atom, atoms can actually share multiple unpaired electrons with each other. In fact, atoms can share up to 6 electrons between themselves. They can also share 4 electrons or 2. We have names for those kinds of interactions. A 2-electron interaction is referred to as a single bond. A 4-electron interaction is referred to as a double bond. A 6-electron interaction is referred to as a triple bond. And whether we have single, double, or triple bonds, again, comes back to the Lewis structure. In the case of the chlorine, they are only sharing 2 electrons with each other. We would describe the bonding in this chlorine molecule as a single bond. And we would depict that as a single line between the 2 atoms. Just as another example, let's look at oxygen. Oxygen also bonds with itself, makes diatomic molecules. If I look at the Lewis structure of oxygen, I'll find that each oxygen has 6 valence electrons. If I start to pair up the unpaired dots, like so, I would see that there are 4 electrons in total being shared. Those 2 here and those 2 there. 4 electrons being shared, we call that a double bond. We depict a double bond as a set of double lines between the 2 atoms. And then again, I've got 4 unbonded electrons on each oxygen. So if I look at the oxygen on the left, I can see that the oxygen on the left has these two, and these four for a total of 8 electrons. The oxygen on the right has these two, and these four for a total of 8 electrons as well. The double bond satisfies the octet for both of the oxygens, allowing it to become stable. So how do we go about doing this for ourselves? How do I look at a chemical formula and know exactly what the bonding is going to look like in that molecule between those atoms? Well, the general process here is relatively simple. If I look at the Lewis dot structure for a given atom, the number of unpaired electrons in that dot structure is going to be equivalent to the number of bonds that it's going to make. So as we saw in the previous slides, the oxygen made 2 bonds because it had 2 unpaired dots. The nitrogen will make 3 bonds because it has 3 unpaired dots. The carbon has 4 unpaired dots, so it's likely to make 4 bonds. Now, what's interesting about the carbon is that it will not make 4 bonds with itself. Something that gets often asked is, well, is there such a thing as a quadruple bond? And the answer there is not really. There are some rare exceptions involving some of the goofy metals in the middle of the periodic table that have been known to exhibit quadruple bonding, but they are very, very rare circumstances. Among nonmetals, triple bond is about as good as it gets. And that's because they fall into these general guidelines overall. The number of unpaired dots is the number of bonds that it forms. For carbon, what we see carbon do is instead of forming diatomic molecules with itself, it tends to form what we call a network of covalent bonds. So those 4 unpaired electrons in carbon usually go out and grab 4 other carbon atoms, which in turn grab 4 other carbon atoms, which in turn grab 4 other carbon atoms. And they make this big network of these carbon atoms that are all attached to 4 other carbon atoms. And in its purest form, the end result is something that we know of as diamond, where all 4 of those bonds arrange themselves in this very perfect crystalline structure. And because of the rigidity of that, we get one of the hardest materials known to man in the form of diamond, as opposed to this diatomic molecule that we see for a lot of the other nonmetals. So how do we bridge? How do we go from Lewis dots, individual atoms with the dots around them, to Lewis structures where we have molecules that consist of all of these atoms tied together with these bonds? Well, one of the reasons why we do it is to get an idea of what the electronic environment is around a particular substance. How many bonds exist? How difficult is it going to be to break those bonds? What kind of physical properties are we going to have? Are we going to have something that is in a high melting point, high boiling point, or is it going to be relatively weak? Is it going to be fragile? All of these things that we can derive based upon knowing what the 3-dimensional structure of a given molecule looks like. So how do we do it? process here is relatively simple. First of all, we want to start with the total number of valence electrons. So I look at the chemical formula, I add together all of the valence electrons based upon where it is. So I've got carbon, carbon's got 4 valence electrons. I've got hydrogen, hydrogen's got 1 valence electron. I've got bromine, bromine's got 7 valence electrons. I put all of that information together. Now, why do I do that? It's a self-check. I want to make sure that at the end of the process, I've drawn it correctly. And the way that I can check that is to make sure that the number of electrons that are supposed to be there are there. The second step is determining the central atom. Now, the central atom is going to be the one with the most unpaired valence electrons. So the easiest way to think about that is start at the carbon group and go right. The carbon group, if I've got something out of the carbon group, it's going to be the center atom. If I don't have something out of the carbon group, I look in the nitrogen group. If I don't have something out of the nitrogen group, I look at the oxygen group. If I don't have something out of that group, I look at the halogens. The next thing I do is to draw the Lewis dot symbols for every element in the compound. And once I do that, then I start linking them together. I take that center atom, I start linking it out to the unpaired electrons of the other atoms. And then I redraw it by putting lines in the place of those dots that were linked together. Give you another minute to copy that down if you don't have it already. It is a possibility. Certainly, as we get to more complex molecules, that would be the case. In that case, what we have is something called a molecule with multiple centers. You would not be asked to draw molecules that have multiple centers. However, understand, we're doing this from a very simplistic kind of sense. Obviously, molecules, covalent compounds are going to get much more complex than this. But the general principle would be the same. So, say that I had, ethyl alcohol. Well, ethyl alcohol, C2H5OH, that's got 3 different centers in it. You've got a carbon, and an oxygen that all act as centers in that particular molecule. But the way that you would construct it would be the same. You just end up linking centers to each other and then kind of filling them out after that. Again, I'm not going to ask you to do anything that complicated, but if you can kind of understand it at the simple level, it doesn't get too much more difficult than that, other than we're just adding more on top of it. So let's do a couple of examples. So with hydrogen, each hydrogen has 1 valence electron. So there's only going to be 2 electrons total in hydrogen. This is what we would call the simplest example. Because hydrogen, group 1, has 1 valence electron. And so all that we would have to do is link together those two unpaired electrons. The resulting molecule would look like that. H single bonded to H. There are no other peripheral dots. Now you may be saying to yourself, well, this isn't an octet. Remember, hydrogen and helium do not obey the octet rule because they're in that first energy level. The first energy level only holds 2 electrons. So for hydrogen and helium, we're only looking for 2 electrons. That single bond provides those 2 electrons. Now, where does this come in here? This is a check for ourselves. The structure that we drew should only have 2 electrons in it. It only has the single bond. Each bond is worth 2 electrons. So we've met that criteria. Now, if we didn't, then that would be a cause for us to look back and make sure, okay, did we calculate the number of electrons correctly? Or did we make a mistake? Did we forget to include a couple of unbonded electrons somewhere along the way? Those are the 2 directions that we can kind of go. So this is a self-check. Technically, step 1 is not necessary, but it's a great way to check ourselves to make sure that we are drawing these correctly. All right, let's look at water next. With water, I've got 1 valence electron for the hydrogen, and there are 2 hydrogens. And oxygen is in group 16, so 6 valence electrons there, total of 8 in the structure. I'm going to draw out my hydrogens and my oxygen with their Lewis structures. Hydrogen, 1 dot. Oxygen, 6. 1, 2, 3, 4, 5, 6. A word of warning, hydrogen is never a center atom. Since it can only form 1 bond, it is pretty much limited to being on the outside always. So hydrogen's always going to be the last pick to be a center atom. It bonds with itself. It makes single bonds with everything else that it encounters. Now from this standpoint, I'm going to link together the unpaired electrons going from oxygen out to the other hydrogens. And when I do that, I see that I'm going to form a single bond between oxygen and hydrogen there, and another single bond between oxygen and hydrogen here. So there's my Lewis structure. Now let's check it. I'm supposed to have 8 electrons. How many electrons are showing in that structure as drawn? Okay, Rachel and David have both said 4. Anybody else say anything? I have no dots showing, so none from there. I've got 2 bonds showing. Each bond is worth 2 electrons. 2 times 2 is 4. So this structure, as drawn, only has 4 electrons in it. Again, this is why we check ourselves. If I had drawn it this way and left it at this would be incorrect because it doesn't show all the electrons that are in the molecule. To do that, I gotta remember to include those lone pairs that did not participate in the bonding. So with those in place now I've got 4 dots and 2 bonds. 2 times 2 is 4. 4 plus 4 is 8. Now I've got 8 electrons, which matches the 8 electrons I'm supposed to have. I now know that this is a correct structure. So can we see the difference? We have to make sure that we include all of the electrons in the structure, not just the bonds, not just the dots, but all of them. All right, let's move on to carbon dioxide then. With carbon dioxide, I've got carbon, which has 4 electrons, and I've got 6 electrons in each oxygen. Total here is going to be 16 electrons. If I draw this out, I'm going to have oxygens and a carbon. The carbon's going to have 4 dots. The oxygen is going to have 6. Which is going to be my center atom? The carbon or one of the oxygens? Okay, carbon. All right, Adria, why carbon?
Because on all 4 slides, there's not any pairs.
That's exactly it. We have the most unpaired electrons on the carbon. And so that's what's going to help it to link up with everything else. So from carbon, I'm going to link together unpaired electrons. So I can see that I've got those 2 sets of electrons between the carbon and the oxygen on the left. I've got 2 links between the carbon and the oxygen on the bottom. I'm going to redraw this. Oxygen, double bond, carbon, double bond, oxygen. And I'm going to remember to put in all of my dots. So this oxygen needs 4 dots. This oxygen also needs 4 dots. Now let's frame it in and see how many electrons that we're dealing with. So I'm going to go to my highlighter here and see if I can't figure it out. Okay, I've got 2, 4, 6, 8, 10, 12, 14, 16. I've got 16 electrons here, which matches the 16 I'm supposed to have. I know that I've drawn the correct structure. So there are 2 real keys to this. The first key is that you have to draw the Lewis dots correctly. And the second key is once you have that, you need to link up the unpaired electrons with each other. And it should kind of fit together like a really nice, well-fitting puzzle. There should be exactly the amount of unpaired dots present to fit all of the needs of all of the atoms. At least as far as the examples that we're going to do will be concerned. All right, any questions with these three examples? All right. Now here's the part that you've been waiting for. Go ahead and try it yourself. So I've got chlorine, I've got methane, and I've got silicon dioxide. Try to draw these three molecules using the techniques that we've just been talking about. All right, so I'm going to go now and share the correct answers for these three. If you're still drawing, that's okay. You can come back to these over the weekend and try to figure out how we got here if you didn't figure it out yourself already. Now, one thing I want to point out to you with regard to silicon dioxide, it should look, oh, I'm sorry. Silicon dioxide should look really familiar to you. And the reason why is it's essentially the same structurally as carbon dioxide. Why is it essentially the same structurally as carbon dioxide? Well, look where carbon and silicon are. They're in the same group, right next to each other. Remember how we talked about bonding and familial kinds of relationships? Well, that's all there. So within this chapter, I've got a couple minutes left. There is one other concept that needs mentioning. It's the concept of electronegativity. Now that we've talked about covalent bonding, we need to talk about how those electrons are actually shared. Electronegativity tells us whether an electron is going to be shared evenly in a bond or disproportionately. Because the more alike the electronegativity is between those two atoms, the more evenly they will share electrons. The more disproportionate it is, the more uneven that sharing will be, and it'll be pointed toward the thing that has the greater electronegativity. So the more electronegativity that something has, the more likely it is to draw electrons to itself in a chemical bond. And the consequences of that electronegativity difference are twofold. We can either get something called polarity, where we have a covalent bond that has a slightly negative side and a slightly positive side, or the electronegativity difference is so great that we actually see a complete transfer of electron and we get an ionic bond instead. If there happens to be no difference in electronegativity, what we will see instead in that case is something called a nonpolar bond. And so there's more about this to come. We don't have time to talk about it today. I don't want to run over on you guys. So What I will do is I'll put together probably a short 10-minute presentation on this. I'll attach it as something to kind of look at to help you review through chapter 8. And that'll allow us to get into chapter 9 coming next week. So we'll look at it. We'll kind of revisit it. If we have questions about the extra material, bring those questions with you on Wednesday. We'll talk about that first thing on Wednesday. Have a good weekend.